Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 23, practice session number 5, which I titled Inversive Geometry and New Proof of Existing Theorems, because in this practice session we will solve our next problem, number 24, in which we are asked to do precisely that: use the newly learned material about inversive geometry in order to generate the proof of a pretty old theorem known as the Ptolemy's theorem, which provides an analytic criterion for four coplanar points to belong to one and the same circle, and which states that in any cyclic quadrilateral, the sum of the products of the lengths of the opposite sides is equal to the product of the lengths of the diagonal of such a quadrilateral. And pictorially, that means that if we're given four distinct coplanar points, named, for example, A, C, D, B, and taken in this particular order with respect to each other, then if such 4 points belong to one and the same circle, named S, then the following analytic criterion or analytic condition holds, and that condition is color-coded, which means that the terms of that expression that have a particular color match the sides of the cyclic quadrilateral. For example, the sides AC and BD are shown in blue, AC and BD are blue. The sides AB and CD, AB and CD are shown in olive green, and the diagonals AD and BC, AD and BC are shown in pink. Strategically, we will solve this particular problem using the so-called transform and conquer problem-solving approach. Transform and conquer problem-solving approach, which we studied in great detail in a dedicated manner on this channel across episodes, season 1, episodes 3, 4, 5, 6, and 7, 5 episodes in total. If you missed those episodes, we highly recommend that you use the season guides, the free PDF files, which contain the links to all the episodes that we produce on this channel, and use the season guide to locate these episodes and work your way through them. And tactically, for a successful transformation, we will use evidently inversion of the parent plane with respect to a circle, and we explained how this can be done in episode 10, seminar 1 on this course. And the way we can arrive at a successful parameters of inversion in this case is as follows. When the 4 points are presumably are given in such a way that they sit on the same circle, then of course the Euclidean distance measured between the relevant points is across a straight line. From, for example, the distance from the point B to the point D and the distance from the point D to the point C is measured over the so-called minimizing geodesic. The minimizing geodesic in the Euclidean plane is a straight line, hence the distance between the points B and D, D and C, for example, is measured across the straight lines. However, in our case, the points, the 4 points that are coplanar and fixed, A, C, D, B, are not just given to us in vacuum. They belong to one and the same, or allegedly they belong to one and the same geometric object, the circle S. So the question is it possible to somehow make the difficult other distance between these points, or the distance measured along the arc of the parent circle, be taken into a situation or a setting where this distance is not as difficult and much more convenient to deal with? And the answer is yes, of course. This is exactly what we studied in the previous lectures and seminars. We remember that any circle that passes through the center of inversion under any power of inversion, be that power positive or negative, is taken into a straight line that does not pass through the center of inversion, and conversely, any straight line that does not pass through the center of inversion is taken into a circle that does pass through the center of inversion, be the power of that inversion negative or positive. And what does that mean? Well, look at this. When a circle is taken into a straight line, it means that in some sense, all the points that make up that circle are straightened out, intuitively speaking, or they sit on one and the same straight line. Consequently, in our case, we can actually pick any given point, either the point A or the point C or the point D or the point B, to play the role of the center of inversion. For demonstration purposes, I will pick the point A. Let's say A is the center of inversion, and the circle of inversion, C, shown over here in white. I did not emphasize that circle too much in order to not make sure that the circle does not fight with the other material. You understand, this is the circle C. A is the center of inversion, and the stipulation here is that the radius of inversion in this case we pick to be strictly larger than the diameter of the parent circle S. That is why you see non-zero distance between the point that is closest to the circle S, the parent circle that houses the four distinct coplanar points. And that is the important detail over here, because now once we execute the inversion with positive power of the parent plane in the circle that has the point A as its center and the radius strictly larger than the diameter of the parent circle S, what will happen? The point A will be taken into the point at infinity. Conversely, the point at infinity will be taken into the center of inversion. So the point A, so we will have one point over here. The point B is taken into the point B prime. The point C is taken into the point C prime. D goes into D prime. And remember, this is our fundamental technical find. The circle S that houses all four distinct coplanar points that passes through the center of inversion is taken into a straight line. The circle S is taken into a straight line S prime. I try to show it in yellow. This is the straight line right here, S prime. And the stipulation here is that our points B prime, C prime, D prime belong to that straight line A. This is where we win tactically, because now the distance between the images of the points B and D, D and C, that is curved, let's say, in the original difficult to solve problem, is now straightened out evidently into a straight line. And it is important to understand that the way in which inversive geometry works is the following. If the point D does not belong to the circle S, then the image of that point, the point D prime, does not belong to the straight line S prime. And conversely, we know that any point that sits on the straight line S prime will be reflected back into a point that sits somewhere on the circle S. Consequently, if the point D prime does not belong to the straight line S, and it's located in either half plane into which the straight line S prime partitions the parent plane, then the pre-image of that point, D, will not be located on the circle S. Consequently, we now have the following statement. 4 points, A, C, D, B, under the chosen transformation, under the chosen inversion, belong to one and the same circle S, if and only if the points B prime, D prime, and C prime belong to one and the same straight line, which we named S prime. And if the point D does not belong to the circle S, then the point D prime does not belong to the straight line S prime. And the question now is, how do we convert these observations into actionable mathematics? One way to convert our observations into actionable mathematics is as follows. Forget about the fourth point, the point D, for example. Let us concentrate on 3 points, A, B, and C. When the 3 points, such as the points A, B, and C, belong to one and the same circle, and when they do not belong to the same circle? Well, we already know an analytic criterion for that particular situation, and we considered a previously solved problem that is not interesting, and the way we decide is as follows. If 3 points are not collinear, then in a way they have no choice, there is no debate. Such 3 non-collinear points define a unique Euclidean, let's say, plane. They define a unique non-degenerate Euclidean triangle, and they define a unique non-degenerate circle. But if 3 such points are collinear, then they do not define a unique plane, they do not define a unique triangle, they do not belong in a circle. And let's say if we again extend our plane with a point at infinity, then such a straight line to which 3 collinear points belong will be in some sense a circle whose center is taken into the point at infinity. But let's say forget about it for a moment. What is the analytic criterion? Well, it's quite simple. We measure 3 distances, A, B, B, C, C, A, X, Y, Z. Then we construct all possible sums of 2 distances, for example, X plus Y, Y plus Z, Z plus X, and we see if any such sum of 2 distances is exactly equal to the third distance. If that's the case, then we have 3 collinear points that do not belong to one circle. And if no 2 distances sum exactly to the remaining distance, then boom, voila, we have our criterion. The 3 points are not collinear, and they define a unique plane, a unique non-degenerate triangle, and a unique circle S. So this is not interesting. We are done in a sense. But now if we bring the fourth point, let's say the point D, now that mere act of adding just one point throws a monkey wrench into the delicate works that our circle S is, because that fourth point D, first of all, it is under no obligation to belong to the parent plane to begin with. It can belong to that plane or not, because remember, 3 distinct non-collinear points define a plane. But let's say the point D does belong to the parent plane. Then it is under no obligation to belong to the circle S. It may belong to the circle S, or it may not belong to the circle S. And in this case, we want to consider the following situation. Let's say we already picked the point A to be the center of inversion. The power of inversion is positive. The radius of inversion is strictly larger than the diameter of the circle S. That means that the straight line S prime will have precisely 0 points in common with the circle S, because this is the non-trivial distance right here between the point that belongs to the circle of inversion and our parent circle S. Well, then we already took the point A to be the center of inversion. We consider it fixed, and across the remaining 3 points, we will take it that the points B and C are also fixed. Why? I just explained why. Because with 3 distinct non-collinear points, we know everything that there is to know about them. We know the analytic criterion. The sum of any 2 distances should not be equal to the remaining distance. So that means that with 3 points A, B, and C fixed, we have 1 point, the bone of contention, so to speak, the point D. To travel will make it not fixed, will make it a variable point. It can travel along the circle S, the parent circle S, and that means that if the fourth point D is on the circle, it will somehow travel along the image of that circle under the chosen inversion along the straight line S prime. And here we have only 3 choices for the mutual juxtaposition of the point D prime on the straight line S prime with respect to the points B prime and C prime. And these three choices are shown here, here, and here. In the first case, evidently, you see, this is where we realize our tactical gain, our tactical win. The point D prime is located in between the points B prime and C prime. The German-born mathematician David Hilbert put together more than 100 years ago or so 22 or 23, I believe, axioms of geometry. And in one of the sections of this axioms, he defines the notion of in-betweenness. So in the sense of David Hilbert's axioms of geometry, the first choice is when the point D prime is located between the image points B prime and C prime. So if the point D belongs to the circle S, and we do have an interesting, non-degenerate, meaningful, or meaty case of a cyclic quadrilateral to speak of, then we already know under chosen inversion, D goes into D prime, and then we have the following partition of the line segment B prime, C prime. This is the largest, in a way, line segment across the three line segments. And this line segment is partitioned or tiled tight with no gaps and no overlaps by the point D prime into the following two line segments. The line segment B prime, D prime, B prime, D prime, and the line segment D prime, C prime, D prime, C prime. The sum of the length of these two line segments produces the line segment B prime, C prime. And there are only two other choices for, remember, the points B and C are fixed. Their images B prime and C prime are fixed. Correspondingly, we have only one runner point, D prime, so the remaining choices are only what? Only two choices. The point D prime is located to, let's say, logically, to the left of both of the points B prime and C prime, or in a sense, the point B prime is located in between the points D prime and C prime. In this case, we have this relation for the distances. The distance from the point D prime to C prime is partitioned into the sum of distances D prime, B prime, and B prime, C prime. B prime and C prime. And the other case is the point D prime jumps to the other extreme. Logically, is located to the right of the fixed points. Again, right, left, it's all logical, up and down, or outside. Or we can say, in terms of David Hilbert's in-betweenness axioms of geometry, the point C prime is located in between the points B prime and D prime. Consequently, the partitioning is shown over here. B prime, C prime, the distance B prime, C prime, plus the distance C prime, D prime. C prime, D prime is equal to the distance B prime, D prime. And the reason for going through this exercise is to show that this is an exhaustive enumeration of mutual juxtaposition of the points of interest. There are no other ones, and no matter what juxtaposition of the runner point D prime we choose, we always come up to one and the same idea of partitioning the length of the larger line segment in terms of the smaller ones, and renaming the points accordingly. We can always converge our situation to just one distance relation that will be the workhorse of our reasoning. And lastly, one important point, that if the point D does not belong to the circle S, and we do not have a meaningful and interesting cyclic quadrilateral, then the point D prime does not belong to the straight line S prime. The point D prime roams the plane somewhere located, being here or whatever. And this is the notion of this is where the notion of minimizing geodesic comes into play, which in some sense captures the structure in a way, or in plain English, the way the Euclidean geometry works. Again, in plain English, a minimizing geodesic is a curve in a given space that minimizes the distance between any two distinct points, which means that if we find a continuous way to connect or plow a path between 2 points in a given space, the minimizing geodesic will provide the path of the smallest length possible between two such points. For example, in the space called a sphere, the minimizing geodesic is the shorter arc of a great circle that runs through these 2 points, and in the Euclidean place, the minimizing geodesic is a straight line, which means that if our point D prime does not sit on the straight line S prime as shown over here, it jumps off into this half plane or that half plane. It's irrelevant. The thing is, the distance between the points B prime and C prime, this distance is no longer partitioned into the sum. It's no longer this. And as I said before, in some sense, this situation brings front and center the structure or the way the Euclidean space works. Here we have the so-called triangle inequality, which is a fundamental technical criterion for the distances as they are measured in the Euclidean space. Look at this. The distance between the points B prime and C prime, remember, it belongs to the minimizing geodesic in that space. And that distance minimizes any other continuous way to get from this point to that point. If the point D prime does not belong to the straight line S prime, then the distance from the point, let's say, B prime to the point C prime that takes a detour through the point D prime will necessarily be larger. The distance B prime D prime plus D prime C prime will necessarily be larger than the distance provided by the minimizing geodesic. This is important to understand. And in this case, one more time, the path that runs from the point B prime to the point C prime is continuous. It is a polygonal line, but we do not skip a bit, we do not miss any points in the plane. We travel from the point B prime to the point D prime, from the point D prime to the point C prime. This is a continuous set of points, but the sum of these distances will never be exactly equal to. It will be strictly larger. That is the important bit. I will take a break right now and erase this material, prepare it for the next step. I will move this relation over here. We will keep these two relations front and center, but no seminar or no practice session is complete without some form of animation and demonstration. And in order to show you that the discussion that we just had has a meaningful visual representation, I put together a demonstration where I wiggle the point D prime along the straight line S prime. Technically, I move the pre-image point D over the arc of the circle S like this. You will see it going left and right, and the point D prime runs along the straight line S prime. But the important thing to understand over here is that going back to the idea that I put forward at the beginning of this segment, if the points A, B, and C are fixed and are not moving in any way, shape, or form, then these 3 points is already enough to produce a favorable situation for us. Such 3 distinct non-collinear points define our parent circle S. We grab our point, any one of these vertices, say the vertex A as the center of inversion, power of inversion is positive, radius is larger than, and then that is enough to lock in this straight line S prime, you see. And then the position of the point D prime, the specific position of the point D prime on the image straight line S prime is in some sense irrelevant, because regardless what it is, we can pick any one of these relations shown over here. And now we can already take this idea. This will be our workhorse relation. For example, we can number this. If this is our relation number 1, let's mark it number 1. This will be number 2. This will be number 3. This will be number 4. So we cross these, and this will be number 5. Across these relations, we will work with this relation and with this relation. Again, bear in mind what is about to transpire. What is about to transpire is that we will show that if the point D does belong to the circle S, and we do have a meaningful cyclic quadrilateral, then this will hold, and we will spin this idea tactically and creatively in a few seconds. But if the point D prime does not belong to the circle S, then the image does not belong to the image straight line S prime, and this relation holds. In summary, if the point D, the fourth point, does belong to the circle S, or if the fourth point D is co-circular with the previous 3 points A, C, and B, then the following distance relation holds. And even though there are other possible mutual juxtapositions of the point D on the circle S with respect to the points B and C, and of the point D prime on the straight line S prime with respect to the points B prime and C prime, as we saw before, by renaming the points correspondingly, this distance relation can always be obtained, and it actually technically boils down to this specific relation. And inversely, if the point D does not belong to the circle S, and the point D prime does not belong to the straight line S prime, and using the notion of minimizing geodesic, we know that the equality will no longer hold, and we will have in this particular distance relation a strict inequality, if you will, and the sum of the distances shown on the left will be always strictly larger than the distance between the corresponding points. If you understood, or better yet, generated all the preparatory work that we carried out in the previous segment, that you are in a good shape and you can carry the solution of this problem all the way to the end on your own and do that correctly. What is the next tactical maneuver after that? The next tactical maneuver is to recall this wonderful Theorem 22, which we also refer to ICSTT. Inversion in a circle, similar triangles theorem. Remember the theorem that we proved? Yes, this is a wonderful theorem, which basically, in some sense, we can even call the fundamental theorem of inversive geometry, because according to this theorem, the magnitudes of the corresponding angles are preserved under inversion, but their orientation or direction is reversed. That is why, as a bijective mapping, inversion is known as an anti-conformal mapping. But the corresponding triangles, according to this theorem, are similar. What is corresponding triangles? Corresponding triangles are triangles that are formed by the inversive images under the chosen inversion. And in this case, how many such interesting triangles we have? Well, evidently we have, let's count, the triangle ABC, the triangle ABD, and the triangle ACD, because remember, A is the center of inversion, so we have 3 triangles. And we will need all 3 triangles to work with these 2 relations that we carefully deduce. But again, remember that according to the transform and conquer problem solving approach, the whole idea of bringing in this mechanism known as inversive geometry is to gain a tactical or competitive advantage. We gain the competitive advantage by straightening out the curved distances, not the minimizing geodesic distances that figure prominently in the Ptolemy theorem, but the curved distances between the relevant points. This is where we gained the competitive advantage. This is how we constructed the distance relation shown here, the distance relation shown over here. And in this case, we want the tactical idea now. How do we convert this tactical gain into something that will eventually prove this theorem? Well, the conversion amounts to very straightforward. maneuver. We take this distance relation that is quite childish. It doesn't really take much intellectual voltage to say, this plus this equal to this, duh. But now we want to rewrite this relation over here, the childish relation that we constructed based on a successful inversion. We want to rewrite it in such a way that we get rid of all the primed characters in that relation, and we replace the primed characters with their non-primed versions, B, D, C, and A. That's the tactical idea. That is all there is to it. And we do it based on the Theorem 22, or inversion in the circle, similar triangles theorem. We'll start with the first pair of triangles. I will go over this pair of triangles in great detail, and I will leave it as an exercise to the viewer to go over the remaining two pairs of similar triangles by themselves. So first we consider the triangles A, B, and C, the triangle A, B, and C, and the triangle that is made up of the images of the points B and C, A, C prime, and B prime. And here, remember, is a caveat that I tried to stress when we were proving this theorem. Back in your middle school and high school, you probably or most likely manipulated the names of the vertices that make up the triangle name willy-nilly. You did not really pay attention to the order of the letters in the names, or order of the vertices in the names of these triangles. But now it's time to pay attention to this order, and that order will become very relevant in the theory of permutations, and consequently in the theory of groups, when and if you will be studying the theory of permutations and the theory of groups. Here, the order or the sequence of names of the vertices and the formation of the name of the triangle is important. If we name our original triangle A, B, and C, A, B, and C, then this triangle is similar to the triangle A, C prime, B prime. And why did we choose this particular ordering of the letters in the image triangle? Here, the vertex A correlates to the vertex A, the vertex B correlates to the vertex C prime, and the vertex C correlates to the vertex B prime. Why is that? Well, we establish this correlation based on the equality of the magnitudes of the corresponding angles. This is the heart and soul of the technical essence of the Theorem 22. The interior angle at A, this guy right here, I'll cross hatch it like this, let's say alpha, remains one and the same because this is the vertex that is shared across these two triangles. But the magnitude of the angle beta at the vertex B of the original triangle becomes by magnitude the angle at the vertex C prime in the image triangle A, C prime, B prime, if we name the original triangle A, B, C. Likewise, the magnitude of the interior angle at the vertex C of the original triangle, the angle gamma, percolates or drifts or travels into the magnitude of the angle gamma at the vertex B prime. This is how this wonderful transformation that we're studying, the inversion of the real plane with respect to a circle, works. This is in some sense, the reason we call this a fundamental theorem of inversive geometry, because this is how this transformation acts on the magnitudes and on the directions or orientation of angles. So once we understand that, we will need this material for the next step. But here we carefully write down the following angular relationship between these two triangles. The magnitude of the angle BAC is equal to the magnitude of which angle? Remember that in the naming of the angles, we now have to use the corresponding vertices that carry the same magnitude of the angles that are equal under this transformation. So the angle BAC equal to the magnitude of the angle C prime A B prime, C prime A B prime. Likewise, the magnitude of the angle ABC or beta is equal to the magnitude of the angle A C prime B prime. Lastly, the magnitude of the angle ACB is gamma, and it is equal to the magnitude of the angle AB prime C prime. Once we have this on the books, what is next? Well, the next is our favorite Euclid's Elements, book 6, proposition 4. According to which, in any two similar triangles, the lengths of the sides that subtend equal angles are in the same proportion where the corresponding sides lie against opposite angles. Don't forget that at the tender age of 23, Isaac Newton knew the set Euclid's Elements back and forth as the palm of his hand. And that tells you something about how great technical minds operate as such. Our favorite Euclid's Elements, book 6, proposition 4, has a good buck on the fact that in the similar triangles A, B, C, and A, C prime, B prime, we have the following situation, the following relation going. Remember, we want to get rid of all the primes in the relation shown over here and over here. Consequently, we begin our work on removing primes from the material that is present on the right hand side of this relation and of this relation. We want to remove primes from B prime and C prime and replace this distance with the distance that is present in the original set of points A, B, C, and D. And the way we do it is as follows. We want our prime suspect B prime, C prime to participate in this ratio, and the way we construct it is as follows. Let's say, so the length, the sides B prime, C prime, B prime, C prime, this side, and the side A, B prime, they subtend the angle gamma in the larger triangle A, C prime, B prime. So we write the distance between the points B prime and C prime relates to the distance between the points A, B prime in the image triangle in the same way in which sides relate to each other, the lengths of which sides relate to each other the same way in the original triangle ABC. Well, the sides that subtend the angle gamma, and that is why we wrote down the angular relationship in the previous segment, are what? CB and CA. So now across these two sides, we have to pick the ones that do what? According to book 6, proposition 4, lie against opposite equal angles. The side C prime, B prime lies against opposite angle alpha in the image triangle. Consequently, which side of the pre-image triangle ABC lies opposite angle A? The side CB. So we write CB or BC, doesn't matter. The distance works the same way. And this relates to which side? The side that lies here, the side AB, lies opposite the angle beta. Opposite the angle beta in the pre-image circle lies the side AC. So this is what we write. BC relates to AC in the same way. So here we want to capture this element that sits in the numerator of the ratio on the left-hand side of the equal sign. From here we get this distance BC over distance AC times the distance AB prime. So here we got rid of the prime over which vertex? C prime. There is no primes with C, but now only B prime left. So if you did not solve this problem correctly and on your own, and you were solving it that way, what would be your next maneuver? Well, the next maneuver here is to bring condition 3 of definition 1 and recall that the points B prime and B prime and B are what? They are the images of each other under the chosen inversion. C r greater than ds, positive power, yada yada. And the workhorse of this relation, of this fact, is the following. The product of the distances between the points A, the center of inversion, and B prime, and A and B, is the square of the radius of inversion. That much we know. And boom, we remove the prime from B by saying that the distance AB prime is equal to r squared divided by the distance between the points A and B. We put this result over here for this distance, and voila, what do we have? We completely got rid of the primes in the material that's present on the right-hand side of the equal sign here and the right-hand side of the less than or greater than sign in this relation. And we have the following fact. The distance b prime c prime is the ratio of the distances b between the points b and c and the product of the distances a, b, a, c scaled by the square of the radius of inversion. And if we torture the remaining two pairs of triangles in the same way as we tortured the previous pair of similar triangles, that is the triangles A, B, D, and A, D prime, B prime, and A, D, C, and A, C prime, D prime, then from the first pair of triangles, similar triangles A, B, D, and A, D prime, B prime, we will obtain this relation over here, the distance BD times r squared divided by the product of distances between the points A and B and A and D. This is the relation. We'll remove the primes from this term right here, from this summand, and we remove the primes from this summand in our original relation by torturing the similar triangles ADC and AC prime D prime. We obtain this relation over here. The radius of inversion squared times the distance between the points C and D divided by the product of the distances between the points A and D and A and C. We do it in exactly the same way in which we obtain this relation. I will not spend any more time on it. This is quite straightforward. This is all middle school arithmetic at this point. Again, remember the basic idea over here was to, first of all, apply the transform and conquer problem solving approach. That's number one. And searching for and finding a successful inversion. During that time, we put our mind into a mode that is isomorphic to the mode in which the mind of practicing mathematicians work. In other words, during that time, we acted or thought like a mathematician. After that, all the observations that we made were either not mathematics or lesser mathematics. This is just tactical maneuvering that carries our idea through. But mathematics is manipulation of idea, generation and regeneration, combination and recombination of ideas. An idea is a first-class citizen in mathematics, and that was the time when we acted or thought like a mathematician. After that, what follows over here is, like I said, lesser mathematics. This is just computational calisthenics or tactical maneuvering. So we constructed this relation, removed the primes from the baby observation that we made in the transform setting. In other words, this relation over here represents a solution of the transformed problem, which is straightforward. Now we reverse transform the whole thing, and we do it by removing the primes from all the material presented in this baby observation. We come over here. Remember that the real number r is greater than the diameter of the parent circle S that presumably or allegedly houses all 4 points A, B, C, and D. It is strictly larger than 0. Then it is a completely legal maneuver to divide this relation through by the square of the non-zero real number. The radius of inversion makes its star appearance. It enters the stage, does something interesting, and then leaves the stage as if it was never there. And all we have to do is multiply the result with cancelled or divided through by r squared with this animal right here. This is the product of all the distances from the point A. Remember, the point A is our center of inversion. We took it to be the center of inversion. So from A to B, from A to D, and from A to C. So their product. And why we do it? Well, we want to clear the denominators in our relation that is a snapshot of the original one in this relation. And once we do it, let's see what happens. On the left-hand side, the leftmost summand in the denominator has AB times AD. The distance is off. AB times AD, so what survives? AC. So AC goes in the numerator. Look at this, the distance AC times the distance BD. Boom, this is our distance that we were looking for. Wonderful. The next summand, we're moving left to right. distance AD times the distance AC. Where is it? ADAC is gone. The distance AB survives. So AB goes into the numerator. AB times CD. AB times CD. Look at this. AB times CD. So now let's see what survives on the right-hand side. On the right-hand side, we have in the denominator the distance AB times the distance AC. AB, AC is a goner. AD survives, percolates into the numerator. AB times BC. AD times BC. And what that means is the following. If the point D is on the circle S, then this relation holds. And if the point D is not on the circle S, then remember, we took this relation and using the notion of minimizing geodesic, we claimed that this must be the case. So this relation percolates into this if it is not the case that D belongs to S. And now we wrap all this magic into the following statement. What we just did is we proved the following theorem. The points A, B, C, and D, if the points A, B, C, and D belong to one and the same circle in such a way that the points B and C sit on opposite or different arcs delineated by the points A and D, then the following relation holds. In other words, if the points A, B, C, and D belong to one circle with the points B and C sitting on the opposite arcs delineated by the points A and D, then this relation holds. And if the 4 points A, B, C, and D do not belong to one and the same circle, then this relation happens. And now what we do next is a short exercise in formal logic. Technically, we just proved the following two statements. If the 4 points A, B, C, D are positioned on the same circle in such a way that the points B and C are located on the opposite arcs delineated by the points A and D, then the following distance relation holds. And that means we prove if P, then Q. The P, the premise is the location of the 4 points on the circle with the condition that the arc this and that and so on. And the consequent is Q, which means that this distance relation holds over here. We also proved that if the 4 points are not located on one and the same circle, then this distance relation holds, and this statement over here is actually the inverse of this one. In other words, we proved that if not P, then not Q. And any if X then Y proposition is logically equivalent to its contrapositive. And how do we form contrapositives? The way we form contrapositives is as follows. We either rotate the predicates that are located between these two keywords, if and then, around the then clause, and then we negate them, or first we negate these predicates and then we rotate them about the then clause. In this case, let us construct the contrapositive for this if X then Y implication. So we will write it as follows. If not P, Q, I'm sorry, and then not P. That is how we did it. We, let's say, rotated the predicates not Q over the clause then, and we said, and we negated it then, not Q, and then we rotated the predicate not P over the then clause, and then we negated it not P. But two negations in a row here and here produce what? They dissipate each other. So what we proved is the following. If Q, then P. And now if we take this implication and this implication, then together with this, what did we just prove? if P then Q, and if Q then P. In other words, we proved that P if and only if Q. And if we convert all this into this lengthy verbiage, which I'm not going to do, then we will have our theorem if, or let's say the points A, B, C, and D are located on the same circle in such a way, points B and C, arcs A and D, yada yada, blah blah blah, if and only if this relation holds. But look at this: if the points A, B, C, and D are located on the one and the same circle, then what does that mean? That means that our quadrilateral ABCD, named appropriately, is cyclic. And if the such a quadrilateral is cyclic, then this here relation holds, and this is precisely the symbolic manifestation or the symbolic embodiment of the Ptolemy's theorem, and the game is over. Again, if anything is not clear, the comment section is open. Ask your question away. This seminar is based on the corresponding chapter of my free book, Inversive Geometry for All. The link to that chapter is in the comment section. Click, pop it open in a separate tab in your browser, read through. But in the lightning round, remember how it pays to go over the proof that we just constructed and comprehend it in a one uniform way. Basically try to squeeze all the technical details, all the technical ideas that we presented in this episode into one short paragraph. Basically, inversion, straight line, similar triangles, book 6 proposition 4. In similar triangles, the lengths of the side about equal angles are in the same proportion where the corresponding sides lie opposite equal angles. We tortured 3 pairs of similar triangles in this case using what? Using theorem 22, inversion in the circle, similar triangles theorem. We produced our baby observation for the partition of this length of the larger line segment, that is a composite quantity, something plus something. And then we removed the primes by expressing all the material in this baby or transformed distance relation into the material that has no primes. And these are precisely the usual suspects of our Ptolemy's theorem. And voila, the only caveat here is that we had to carefully roll through if P then Q, and we had to prove if not P then not Q. You see, this is the important bit. And then we seek a little bit of formal logic onto it. Negate, rotate, construct the contrapositive. The contrapositive is actually the other side of our if P then Q, if Q then P, if and only if, and there you go. If the 4 points belong to one circle, Ptolemy's theorem holds, game over. This is precisely how we applied newly learned material to the proof, to the process of generating a proof of the existing theorem. This theorem is quite old, more than 2,000 or roughly 2,000 years old, let's say, and this is how we did it. Now, this is it for the problem 24, and this is how, in a way, we generated a new proof of the existing theorem. And when we were trying to fit the new material into the proof of the existing theorem, this is precisely how the theory goes, improved our understanding of how inversive geometry works. This is the point of these exercises. You look at certain problems, and at first blush, they seem to have nothing to do with inversive geometry, but precisely in this part of the course, we practice applying newly learned material to the process of solving problems and generating proofs. Now, this is it, like I said, for this problem, for the problem 24, and for practice number 5. And for the next practice, bring your mechanical engineering hat, because in the next practice session, we will work on a quite interesting problem that deals with the so-called Poiseuille-Lipkin linkage.